Okay, okay, fantastic. Yeah. To close the day, we have Seb, who's going to be talking about locality of supercritical percolation. All right, over to you, Seb.
Thank you. Yeah, so as you know, the function theta is an interesting function in percolation theory. So yeah, given a parameter p, it gives you the probability that the origin lies in an infinite cluster. And some interesting question in percolation theory arise as follow. Like, what is the regularity of this map? And so, yeah, there are nice theorems or conjectures in this direction. And today I would like to speak about this topic, but with a twist. So, yeah, actually here, I've not really defined the function because I've not told you on which graph I work. So if we were to be more precise, I should specify on which graph I work. So rather, I have defined the family of functions. On this, we can think of it as instead of a family of functions, it can be a function with two variables, the parameter, but also the geometry. And then we can play the same game, like these two variable maps. Can we study its regularity? Yeah, today I'd like to tell you a few things about this question. So, yeah, this is the story I'm going to tell is joint work with Christoforos Panayotis from the University of Bath. And yeah, I'm happy to share some mathematical thoughts with you today, which could not be possible without this event occurring. So big thanks to the organizers and the ICTS for this wonderful percolation conference. Yeah, if I'm not speaking loud enough or whatever, just interrupt me and let me know. Okay, so let's get started. What is the setup for today? So yeah, percolation-wise, like probabilistically, it's as usual, like basic definition, Bernoulli bond percolation. Regarding the geometry, let's just be explicit about our assumptions. So our graphs, so what is the dress code for our graphs? So they are taken implicitly to be simple. So no self loops, no multiple edges, no orientation on the edges. We don't really care about the empty graphs, so we have at least one vertex. Take locally finite graphs, each vertex has finitely many neighbors. And we take graphs to be connected. Okay, so this is a very weak dress code, like we tell the graphs not to come naked. Now let's ask them to suit up a little. So we will have other assumptions on top of that. So on top of these tacit assumptions, let's ask for transitivity. So we want the geometry to be homogeneous. So yeah, I briefly recall that transitive means that if you sit at a vertex or at another vertex, you just see the same rooted graph, which can be formalized by saying that any vertex can be mapped to any other by a graph automorphism. And with this additional assumption, we have a nice theory of percolation, many theorems, nice conjectures. It's a more structured setup. But given what I want to study today, it will not be enough because we will want to study like fine questions, and also we want to have answers and not only conjectures. So additionally, we will ask to have the graph. We'll ask for our graphs to have polynomial growth, meaning that the cardinality of the ball is upper bounded by a polynomial in the radius of the ball. So this definition does make sense. Like the graph is non-empty, so we can pick a root. The graph is transitive, so the choice of root doesn't matter. And Okay, and if we have transitive graphs of polynomial growth, then we have even more structure on our graph. Actually, it will be useful to us to speak of the dimension of such a graph. To speak of it, it's useful to remind a nice theorem from the geometry of groups. So by combining results from the 70s and the 80s due to Bass, Givarch, Gromov, and Trofimov, we can say that there is a unique non-negative integer such that the cardinality of the ball behaves as n to the d. So big O n to the d in both directions. This is, if I need at some point to refer to the dimension of the graph, it's this little d that I have in mind. Very last item in the dress code, we will be interested in supercritical percolation. And for that, it's useful to be in dimension strictly more than 1. So, which, given the assumption above, is just the same as PC smaller than 1. It's also the same as being one-ended, once again, if we assume all the above assumptions. Okay, so if we summarize a little bit, what we want to study is bond percolation on transitive graphs of polynomial growth with dimensions strictly more than 1. So how does it compare with the usual square lattice, cubic lattice, etc.? So when we work with hypercubic ZD, like the usual graph structure we put on ZD, I call it usual ZD. And usual ZD is, of course, a graph in the sense of what we focus on in this talk. But we can go beyond that. For example, here I've drawn the square lattice. On the square lattice, you can get it by taking this red pattern and copy-pasting it everywhere. But you could start from Z2 or ZD and copy-paste another pattern. For example, like this. For readability, I've not copy-pasted it everywhere. And when we do this, we obtain another natural graph structure on ZD, translation invariant. These are the so-called Kelly graphs of ZD. But in the middle of the process, we lose something. Namely, we lose isotropy. The first graph, we could swap the two edges, like horizontal or vertical were the same. In Kelly graphs of ZD, we have less symmetries, so probabilistically, it's more challenging. Another kind of things we need to take care of when we go to this higher level of generality, transitive polynomial growth, are geometries like this one. So yeah, this is a picture that comes from somewhere. It's a so-called Kelly graph of the Heisenberg group. So Heisenberg group is this group of matrices with integer coefficients. But we don't really need to care about the algebra for today. What we care about is just this picture. So what is this picture? The vertices are displayed as the cubic lattice, but the edges are not as usual. So from left to right, we have black edges. These are not very complicated. But in a transversal direction, we have green edges, dark green. And these are more subtle. So in this plane here in the middle, they are just horizontal. But when I move the plane to the left or to the right, then each time I move by 1, I will have to increase or decrease the slope by 1. So we get kind of a twisted geometry like this. anytime my plane moves, I apply a transvection. And here we have an example of a non-Euclidean geometry. It's not Z2, Z3, or Z4, it's something else. Okay, so yeah, this was about the setup. Now we are going to do percolation. Before that, if there is any question, feel free to ask. Yeah, I won't say it every time, but anytime in the talk, please feel free to interrupt if needed.
Sorry, Seb, just to double check so that I understand it. So you have a graph which is transitive and of polynomial growth, then it must have ball growth, which is like it must have like an integer dimension. You can't have fractal dimension. Is that right?
Yeah, it has to be an integer, which because okay, so yeah, so actually some give out.
Sorry, Seb, you just cut out.
Did were you start from a Kelly graph 1, 2,
Hello. Can you say something? It's the feed is cutting. I don't know if you've got a connectivity issue. Could you just say that again?
Yeah. Can you hear me again? I hope so.
Yeah, we can hear you now.
Okay, thanks. So Basson-Guivarch, they were starting from a Kelly graph of a nilpotent group, and then they proved that they can compute the growth exponent in terms of some algebraic data about the group. So since these are really coming from structure of groups, typically this number will be a rank of an abelian group. This will be something else, but these are explicit quantities which by definition are integers. And
Okay,
then what Gromov and Trofimov did were to say that the other way around, if you have polynomial growth, then you have to be somehow a Kelly graph of a nilpotent group, or you look like it. And so then by using the Basson-Guivarch formula, it turns out the dimension is an integer automatically.
Oh, thank you.
Yeah, thanks for the question. Okay, so let's get started with percolation now. So I will not start directly with question depending on P and G. Let's start with dependence only in P. So fix any graph, so meaning any graph in our setup. I will not say it every time today. So we pick a graph, transitive polynomial growth, dimension more than 1. Is the theta function as a parameter of P an analytic function? So there are certain things to say about it, some more trivial than others. The first point is that it cannot be analytic at PC because it's 0 to the left, it's non-zero to the right. So obviously, theta cannot be analytic at PC. And actually, for physicists, it could be a way to define PC, like looking for places where some function ceases to be analytic. To the left of PC, it's trivially analytic because it's a 0 function. So what is interesting is to ask the question in the supercritical regime. And the theorem we prove is yes. So yes, the function theta is analytic in the supercritical regime for all graphs we study today. So this is not the first result of this kind. So let's give some information about what was known before. So I will only speak about like finite dimensional graphs. And yeah, the starting point was more the usual ZD. And in this setup, Kesten asked in 81 if there was analyticity above PC. And a few years ago, Georgakopoulos and Panayotis have proved that indeed it was analytic. So a paper that got published in 2023. And in the first part of this talk, I would like to explain you how to prove this green theorem, how to prove analyticity above PC. So let's start with naive attempts. Then we will maybe see that they fail somewhere, and we will try to improve. So first, 1 minus theta is more convenient to work with than theta, because 1 minus theta of P is the probability that the cluster of the origin is finite, and finite cluster is a more combinatorial finite structure to work with if we want to have an infinite sum of polynomials. But when we have said this, we have not said much. Then how do we get started? So I see two natural strategies. The first strategy would be to say that this probability is the sum over all finite shapes of the probabilities that the cluster of the origin exactly has this shape. So it is an infinite sum, and each term in the sum is a polynomial finite size event, and the probability is actually the probability that inside the shape everything can be connected to the origin, and outside, like on the shell, the boundary, everything is closed. Okay, why not? Could be one strategy. Another strategy goes as follows. The probability that the cluster of the origin is finite is the same as asking for the existence of a blocking surface. There should exist a shell such that everything is closed around along the shell. But then the origin may be surrounded by different shells. So instead of having a sum, we need to apply inclusion-exclusion. Just, I'm not so sure the terminology is standard for, the formula is well known, but the terminology, so I mean sum of probabilities minus sum of pairwise intersection plus sum of threefold intersections. So this formula. Okay, so these are two possible ways to tackle the question. Let's focus on the yellow one on the right, because on the left we have to control the inside and the outside. And yeah, if we only have to control the outside, it's probably better. So let's investigate this strategy. And to investigate this strategy, we need to make sense of what is a blocking surface. So the graph theoretic concept for this is well known. It's the notion of cut set. So what is a cut set? So a typical letter I shall use for cut set is capital Pi. And the cut set is a set of edges such that any path from the origin to infinity has to use an edge of pi. So yeah, no way to avoid pi if you want to go from the origin to infinity. And it will be useful for us because the event that the cluster of the origin is finite can also be described as the existence of a closed cut set. So a cut set such that all its edges are closed. Actually, there is nothing to lose and much to gain to introduce minimal cut sets, which are simply cut sets that are minimal for inclusion among cut sets. And then we still have this description of the event. K0 is finite if and only if there is a closed minimal cut set. And by doing this, we have much less sets to consider, because like if I have a cut set, adding other edges will still be a cut set, but it's very redundant to do so. So by studying minimal cut set, we trim down the sum tremendously, which will be helpful. And we will also see that minimal cut sets are better behaved anyway. Okay, so let's get started. So we had this yellow strategy. So we need to implement inclusion exclusion. So how do we go? Maybe some notation first. So I denote by Cn the set of minimal cut sets of size n. And if I want just to perform the first sum in inclusion exclusion, what I will obtain is the sum for all n. Sum for pi in Cn of the probability that pi is fully closed. This probability is simply 1 minus p to the n. And so we simply multiply by the cardinality of Cn. So what we are interested in is how fast this quantity grows. It competes with 1 minus p to the n, and we would like it to grow exponentially, and even at a suitable exponential rate if we want this proof to work. So let's see if combinatorics is behind us for this strategy or not. And in order to have an estimate for Cn, we need to understand Cn somehow. So there could be different ways to understand the cardinality of Cn. Some recent works of Isso, Severo, and Tassion could be used for this specific purpose. But there is also another strategy that will be useful for other purposes anyway. So I will speak of this second strategy. Okay, so here is a theorem due to Babson and Benyamini, revisited later by Adam Timar, that gives us some precious information about minimal cut sets. Roughly, it says that the intuition of blocking surface is a good intuition, in that blocking surfaces, we picture them as connected, and indeed, it's true in some sense. So for any graph in our setup, there is a constant t, such that every minimal cut set is t coarse connected. And by t coarse connected, I mean that if we have legs of length t, then the minimal cut set is connected. Okay, so it's a good thing to know. We understand Cn better. We have a better understanding of minimal cut sets, but how does it help with counting, which was our original problem? And for this, I recall some nice folklore fact. So in this fact, H is any graph. We don't care about transitivity, etc. Pick D a number at least 2, or some vertex in the graph, and assume that in your graph, each vertex has at most d neighbors. What we want to do is to upper bound the number of connected subsets of the set of edges, of vertices, sorry. So we look at set of vertices that have n vertices, contain the origin, and are connected. So like lattice animals, I guess. And the result is that this number is upper bounded by this, and yeah, if you want a more concise expression, it's upper bounded by E times D, everything to the n. And E really is exponential of 1. And by combining the two above results, we get an exponential upper bound on Cn, the cardinality of Cn. Because indeed minimal cut sets are connected, maybe not in the original graph, but in a modified graph. And then we know how to bound connected subsets. So we are done, more or less. Technically, we have to work a little bit more, but it's very easy to have a good proof. The cheating comes from the fact that the minimal cut set do not go through a prescribed vertex. They surround the origin, but they do not touch the origin. But it's easy to solve this problem because it's possible to pick a B infinite geodesic going through the origin, and then our minimal cut set has to prevent both ways to go to infinity. And if the cut set itself is connected, it restricts a lot the possibilities for these distances. They have to be linear in n. So actually we upper bound by linear times exponential. So indeed we have an exponential upper bound. So in the end, in terms of control for the estimate when we do inclusion exclusion, we want to control this quantity. Well, it's good and bad news at the same time. Good news because if P is close enough to 1, we are done. And bad news because if P is not close to 1, the strategy doesn't work. Because the constant here, well, we don't control it well. But the good news is really good, actually, because it calls for renormalization argument. If something holds in perturbative regime, we can try to make it work in the whole supercritical regime by renormalizing, and it's exactly what we are going to do. So to this end, it's customary to introduce a notion of good and bad boxes or vertices. So in our case, we will say that a vertex in our original graph is k good if the ball of centered at V and with radius k contains exactly one macroscopic cluster. We don't care about detailed statements, just have this informal description in mind. And k is to be thought of as a constant that will have to be fixed suitably later. So this is the definition of a k good vertex, and other vertices are called k bad. And this notion of good and bad vertices will be useful because it was proved in a paper with Daniel Contreras and Vincent Tation that the probability that a vertex is bad goes to 0. It goes to 0 fast, like stretch exponentially fast. So there is hope indeed to implement renormalization argument. And to implement it, we need some notion of interface. So the typical letter we use for interfaces is I, like handwritten I, calligraphic. And we say that an interface I occurs if I is a T-course connected component of bad vertices such that blah, 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 blah. I don't care what comes after in the sentence. So let's focus on the red part of the definition. So first, interfaces are made of bad vertices. So for renormalization, it's very good because we know that the probability that a vertex is bad is very small. So we are getting kind of in a perturbative regime because of that. And then, like, remember that earlier we had to go from cut sets to minimal cut sets to avoid cumbersome redundancies. Here, likewise, we want to define some sets of bad vertices in kind of a canonical way that will avoid redundancies. And yeah, taking connected components is a relevant way to do so. And the T that appears in this definition is the one of the Babson-Benjamini-Timar result. And then what we want is to have such an equivalence. So maybe we assume that the cluster of the origin is not too small. Anyway, finite size events have polynomial probabilities, so it's not a problem to assume that. And then what we would like is to have an equivalence between the event that 0 is in a finite cluster and the fact that some interface occurs. And then we can try to make inclusion-exclusion over interfaces. And it's in order to have this equivalence that we have to make a more refined notion of interface, because the red part is kind of macroscopic only, but we want to control exactly the cluster of the origin to have an equivalence, an exact criterion for its finiteness. So for that, the notion of interface needs to see something at the microscopic level too. So then, yeah, we have to put some extra condition so that the equivalence is reasonable. Okay, and then with all this, we can work on, at the end, prove the result. And that's nice. So yeah, of course, I've put some dust under the carpet, but I hope at least you can see the carpet. And also, I should say that this interface strategy, so maybe not exactly that one, but the general interface strategy goes to the earlier work of Georgakopoulos and Panayotis. And our implementation is kind of a revisit of this interface strategy in light of the techniques of Contreras, Station, and myself. And it's more or less everything I wanted to say when the graph G is fixed. Okay, so now what can we get when we allow also the graph to vary? So here is a theorem which is essentially the same as the one we've been discussing. So analyticity of theta in the supercritical regime. But now we are trying to prove analyticity in a way that only needs to know a big ball of our graph. And from the knowledge of one large ball only, we would like to deduce already good amount of information. So maybe I should not get ahead of myself and start by introducing the local topology. So given two graphs G and H, I define the matching radius between G and H to be the maximal radius such that G and H have the same ball of radius K. And we define a topology on the space of graphs by saying that two graphs are close if their matching radius is large. And just to get a feeling for this topology, we can take examples of slabs. So, as in Pierre-François' talk yesterday. So, take two-dimension slab in Z3 and make it periodic. Well, if n is very large, you don't see the cycle yet. You are as in the cubic lattice, and it justifies this convergence. Okay, so how do we state some analyticity result in a way that is kind of uniform in the neighborhood of G? So maybe I will give an informal result first, but informally, maybe we would want to say something like, I have a map sending G to theta of G. It goes from my space of graphs to a space of analytic functions. And in some sense, I would like to say that this function is continuous. So can we make a precise statement into this philosophy? So yes, here we go. Pick a graph G and pick a supercritical parameter Q and also some epsilon. Then it's possible to find some neighborhood U of the interval Q1. So you take the interval Q1, closed interval, and U will be a small neighborhood of it in the complex plane. So an open neighborhood connected, and that will be suitable such that what comes next holds. So there is some region U such that for every H close enough to G, so first PC of H will be smaller than Q, but also theta G and theta H admit analytic extensions to U, which are unique, and I denote them with a tilde. And on U, these analytic extensions will be epsilon close in uniform norm. So yeah, can find some U such that we have analytic extensions and they are close to each other. And this is one example of a statement we prove, but actually we can also prove so kind of local. So this, I would say, it's a local version of the analyticity result, but actually we can also prove local versions of other supercritical results, such as supercritical sharpness or study of the isoperimetry of the infinite cluster, anchored isoperimetry. So for supercritical sharpness, I refer you to what was explained in the amazing talk of Piet yesterday, but really nice theorem on proof. Okay. And so what is the new input to obtain such local versions of theorems in supercritical regime? So recall that we had this theorem of Babson-Benjamini revisited by Tima, and this was some external geometric input that was important in the proof. Actually, it was really important in the proof of analyticity, because in the definition of interface, we needed to consider T-coarse connected components. So it was used twice. It was used this theorem to count, to get an upper bound on the number of minimal cut sets, but it's also used in the definition of interface. So this theorem is important in the proof, and to get a local version of it, to get a local version of the analyticity theorem, what we need is a local version of this theorem. And indeed, I managed to put it. And indeed, it's correct. So there is a local version of this geometric result. And this is a new input. And I would like not to sketch the proof, but at least to give a rough view of the structure of the proof seen from far. So how do we prove this local version of this result? So roughly, the structure of the proof goes as follows. We start with a converging sequence of graphs, and then we use recent results by geometers of groups. So here we use a paper by Trishen and Thornton. Yeah.
Seb, sorry, could you go back just a second?
Sure.
I love this. That's fine.
It's okay. So yeah, given a graph, so
Seb, can I ask a question as well?
Yeah, of course.
So the theorem that is just before this one, but you don't have to show it again if you.
Yeah.
But my question is, do you have can you understand how the radius of convergence, so say the diameter of the set U that was defined before, do you have a lower bound on this in terms of properties of the graph G?
So I remember we managed to get something more quantitative in some sense, but if I remember correctly, the quantitative aspect was, I will show it again.
Yes, yes.
The quantitative aspect was more in the close enough part. So it wasn't in the complex plane, it was more there. So maybe by inspecting the proof, maybe it's possible to extract something, but yeah, at least on top of my head for now, just there is some U, and I'm not able to say something much more interesting for now.
I see. Thank you.
Thank you for the question. Other questions for now? So if not, we can get back to the rough structure of the local version of Babson, Benjamini, Tima. So we start from a converging sequence of graphs. And then Tessera and Thornton tell us, oh, actually, these graphs that are yeah, they have just soft assumptions. They are transitive, polynomial growth. They say actually up to quasi-isometry, I can transform them into rigid objects where you have access to algebra, you can use group theory, you have more tools. So what they say is that these graphs are quasi-isometric to Kelly graphs of nilpotent groups, even better, like they can bound some quantities some quantities will be bounded uniformly in N. And it's A quasi-isometric with a fixed value of A. So it's not, the value of A does not depend on N, it's uniform along the sequence. So maybe I should remind what means quasi-isometry. So it's simply a map between graphs that says that the two graphs are kind of the same, except that you are allowed to distort distances in an affine way. So yeah, the map is almost surjective, and we tolerate additive and multiplicative distortions up to A. So okay, now the proof splits in two. We have, so I will start by saying a word about the first half. So there was a question originally in the paper by Babson and Beniamini, and they ask if coarse connectedness of minimal cut sets behave well under quasi-isometry. And we answer positively this question, and it's helpful to complete our strategy. So then remains the task to understand the Kelly graphs of nilpotent groups. And here we can use algebra, some reasoning, and in the end make things work. But the road is not so easy. So in particular, we need to study different classes of minimal cut sets. So yeah, finding a constant T such that minimal cut sets are coarse connected. In the paper, we call these notions cut connectivity. My plan was to call it Connecticut, but Christophoros thought it was maybe not formal enough for a published paper. And then Tom Hutchcroft ruined the day and taught me that it's pronounced Connecticut, but for a French person, it's still funny. And so why do we need to study several variations of cut connectivity? Imagine for a minute that you already understand D3, but you don't understand yet Z2. So yeah, maybe it's a bit weird, but let's assume that for a moment. So in Z3, you understand well minimal cut sets. In Z2, it's not the case yet. Then one thing you can do, here I've drawn a red minimal cut set in Z2. If you want to understand it, one way is to lift it in Z3. You take the preimage. And now you have a nice cylinder, which indeed is connected, and you could try to say that the image of a connected set is connected. But the problem is that upstairs, it's not a cut set, because I can go to infinity in the cylinder. So actually, what you should say is that downstairs, it was a cut set between the origin and some point, and upstairs, it will be a cut set between points, not a cut set to infinity. But so you see, starting from a finite minimal cut set between points, I have to study possibly infinite minimal cut sets between points. So then you could tell me, oh, but maybe it suffices to study all minimal cut sets, irrespective of whether they are finite or infinite. And then maybe this unified notion is enough. But at other places of the proof, it's important to have cut sets that are finite. So yeah, to the best of our current understanding, we can't run the argument with a single notion of cut connectivity. So I am almost done. I just want to state one last proposition which I like from the paper. And for this last proposition, we will work in a restricted setup. So not all transitive graphs of polynomial growth. So we will work with slabs like this. So the infinite dimensions, there are at least 2 of them. And the other dimensions, there can be any finite number of them, and possibly 0. So you can totally work with ZD if you want. And what we do is rephrase the theta PC equals 0 conjecture. We don't solve it. We rephrase it, but it's still funny. So in the above setup, it's well known that theta PC equals 0 is equivalent to theta being continuous in P for every G. So this is well known, but I write it for emphasis. And what we state is that it's also equivalent to this statement. So for every P, the quantity being continuous in G. And it's also equivalent to joint continuity. So I find it a fun result. I like it. And just, I would like, before concluding, to give you a key to understand this proposition, which hopefully could explain why the proposition holds and why we work in this restricted setup. And the key is that if we look at 2-dimensional slabs, they are dense in the space of these graphs. And 2-dimensional slabs are known to satisfy theta PC equals 0. This is a result by Dumesnil-Clopin, Sidoravicius, and Tassion. And so kind of by density, if everything, yeah. Essentially, this is the key input to proving the proposition. Last but not least, thank you very much.
Okay, thanks, Seb, for the very nice talk with the very nice presentation. So does anyone have any questions? No? Any questions on the Zoom? Okay. So yeah, thank you so much, Seb. And yeah, once again, I really like the cutouts. I think that was amazing. So let's thank Seb again.
Thank you.